and I also do accelerator probes, including new experimental proposals. And recently, I also start to, I have always been doing this, but there are some recent topics of interest. One is studying the light axion or light scatter particle effects on trans-Newtonian objects and exoplanet precession, and also small-scale tests for velocity-dependent self-emitting dark matter. And I'll mention some of these in a talk when it's the time to introduce these. Good. So here is the outline of the talk. First, I will talk about the dark matter complementarity of different kind of experiments. And then I will talk about a high energy intensity experiment to focus on these interesting experiments that both have high intensity or high energy, or both. And then I will talk about one model of interest that is related to Hillman's work, actually. And I will talk about finally some vision and future outlook. So dark matter complementarity. If you look at the search for dark matter, you find out there's so many different kind of search for dark matter. And of course, this is not a complete list, but I mentioned some of these more interesting ones that people may be familiar with, or the one that I worked on that I'm more familiar with. But really, there's so many different kind of potential dark matter candidate because we really don't know what it is. So, but there's two major probes. One is Accelerator Probe and one is astrophysical and cosmological search. And people can ask the question, why? Why do you want to search for these two? So I will tell you kind of why from my perspective. And there is also MEV to GeV mass regime that a lot of people are interested in. And I will tell you why this is an interesting mass range to search for dark sector. Okay, but before we get into detail, there is this little comparison that I want to make just to start the conversation. So on the x-axis is the mass of the millicharged dark matter. On the y-axis is the scattering cross-section with electron. So you see that on the left-hand side, the plot has some direct detection bound because you assume the dark matter abundance. But on the right-hand side, you can remove this bound because this is saying that you don't necessarily need to assume the dark matter abundance. This bound, accelerator bound, will always be there because it doesn't care if things are dark matter or not. You can just produce this and detect them. So in some sense, the bound from accelerator is more robust. So let me elaborate on that. So in more detail, you can look at these. There are 4 different kind of search that I list here. There are more, but let's focus on these 4. There's accelerator-based, astrophysical production, direct detection, and cosmology. And as accelerator and astrophysical production, they're kind of more robust because you're really producing this stuff and then detect them in the accelerator one. And in astrophysical production, you produce them in supernova or cosmic ray or things like that. So you directly produce this stuff. So the bound that you set is more robust because if something is in the Lagrangian, you can produce them. But for the direct detection, it's different. And it could be more interesting because these are really searching for dark matter. So the last 2 are really searching for the effect of dark matter. But on the other hand, the bound that you post, you can actually say, even if you post a bound, maybe I can change the abundance of the dark matter to avoid the bound. So that's why, in some sense, it's less robust. But either way, if you combine these, you can really learn the full story of dark matter. So accelerator probe. So in the accelerator, you produce particle, and these kind of is more robust. And there's many existing experiments and many to come, so you can have complementarity to each other. And it doesn't really care too much about dark matter attenuation, which I will tell you what it is. But basically, if you search for local dark matter in the sky or in the nearby galaxy, before they fly into your detector, there's a lot of interaction that could happen, and you might not be able to detect them. Maybe they lose too much energy. So because of that, some of the local direct detection search sometimes cannot see some dark matter. But Accelerator Probe doesn't care because they just produce it. So there's this advantage. But the disadvantage is that you don't know if you're really searching for dark matter. You're producing some stuff, and that's it. So that's interesting. And then further on, I want to focus on the high energy intensity frontier, meaning that I want to have a very high energy and high intensity, and preferably combine both of them. So there's a lot of experiment that something is called proton fixed target and neutrino experiments, and I will explain what they are. They have high statistics because they can put a lot of proton on target. So it's very intuitive. You have a target and you shoot your proton onto the target. So it's called proton on target. And when you have proton on target, you can produce neutrino through the meson decay. So you can study neutrino, and there are also dark sector particles. And these machines have relatively high energy because they have 100 to 400. So they are really the kind of high energy intensity frontier. They're also shielded underground, so have lower background, and there's many of them as well. So you have the strength in number. But furthermore, there's a different kind of thing that is in the high intensity energy frontier. So what do I mean by that? What I mean by that is that you can search for something that is different in the LHC forward regime. So in the past, people have studied a lot of LHC transverse regime. So when I say transverse or then forward, I should have a figure here, but I forgot to put it. But so think about this IP. So IP means interaction point. You have two collisions in this IP. So you have two beams colliding in the IP interaction point. Usually your detector look like this. So it's searching for physics that has large transverse momentum. That's Atlas or CMS that you're familiar with. Oh, actually it's here, right? So you have Atlas, CMS here. But you can say, I don't search for things here. I search for things in the forward region. And that's why there is something called Phaser new, and also they want to build a forward physics facility. So is my internet good? Do you lose my signal, or it's good?
It's good.
It's good? Okay, good. So now the new kind of proposal that are interesting is you put a detector, not here, not in the transverse region, but here, downstream of the transverse region, and actually 400, 500 meters away, but in the forward region, in the roughly along the beam direction. And here you have a lot of flux of meson. That's why you have a good sensitivity for the low, medium energy, low energy compared to the LHC, but still high energy compared to a lot of experiments. So I call these high energy, high intensity energy frontier, because you still have high energy collision, but you also have high intensity because you're in the forward region that you see a lot of meson. So that's the exciting two things that I want to focus on today. And let's also complement these two, astrophysical and cosmological search, because there's a reason why these are interesting. So there's many of them. I will not get into detail, but today I will focus on a small scale structure study. So what is a small scale structure study? So if you ask me, I give you a quintessential or the classical example of these kind of things. So let's look at this paper by Manoj and Chantuling and Heibel. So their idea is that now when you look at different galaxies, you can try to get the dark matter self-interacting cross-section from fitting this galaxy profile. So if you look at their velocity profile, you can try to fit the best self-interaction cross-section that is needed to core the profile. You see the profile is cored, and there's some detail. But anyway, forget about the detail. For different velocity of the galaxy, it corresponds to different scale of the galaxy. So there's dwarf, which is small, low surface brightness, which is middle, and then the large one, which is cluster. And they prefer different self-interaction cross-section. So because of these, you can actually have a model that to fit all of these. And the model is thus very exciting because you can actually have, so this thing shows you the real property of the dark matter, not just the property of some dark sector particle. So that's why this is interesting. Of course, now the story is much more complicated because there's baryonic feedback. So this is in 15. Nowadays, things are much more complicated here. So you have to update this plot. But one day, if you can really differentiate the cross-section here, then you can rule out a lot of the model that I will talk about today. So this is very interesting. This is a small-scale study. Okay, so finally, my intro will bring us to the MEV to GeV dark sector. The reason why you want to study MEV to GeV is because you want to study the signal of these anomalies, and this is where the discovery can come from. And there's many anomalies that maybe you heard about some of these, but I will just list the name. If you're interested, you can search for them. So there's mu1G minus 2 LSND, edges result, and the beryllium small scale structure. They all inspire a lot of the MEV to GeV dark matter model or dark sector model. In particular, there's two of them, the red one I will mention today, and the bold one are the one that I work on. And there's a lot of reference, but the red one and the red one are the one that I'll talk about that is directly related to the dark matter model. So high energy meets high intensity, proton fixed target and forward experiment. Let's get into it a little bit more, okay? So when you have both high energy and high intensity, you can start to study things that are not probed before. Meaning that in the high energy situation, high mass particle, there's a lot of WIMP search. If you don't know what WIMP is, it's fine. Some dark matter, some kind of dark matter candidate that is around TeV or 100 GeV to TeV or above, to 100 TeV actually. So that's the WIMP. There's a lot of high mass search. There's also a lot of low mass search because previously there's a lot of fixed target search that is in a low mass. But in between, that's when you can have these new fixed target experiment to probe. So you can fill up the low mass and high mass gap of the dark sector particle. But neutrino is similar, but neutrino just, you already know the mass, but they have different energy. So you can also fill up the low energy and high energy neutrino scattering gap, which I will also show you later. And there's many different facilities. So I'm at Fermilab. So at Fermilab, there is a booster beam, there's NUMI beam, there's LBNF beam, and I will introduce some of them later. But they are all different kind of beam that have different energy and fixed target and proton on target. But you can see that they all have 10 to like 20, 21 kind of proton on target per year, which is very high compared to the HC, which is 10 to 16. So it's much higher, orders of magnitude higher. And you also have the NA62 and SHIP. They're using the SPS beam. So really, I should just have one beam, but sometimes the experiments are more famous. So I list the experiment as well here. So these are the experimental name, and this is the beam name. It's called SPS. And all these are beam name. Okay. So there's all these kind of facility. Let's get into a little bit even more detail. So for all these kind of experiments, you can consider them to be scattering or decay. So for scattering experiment, they're studying neutrino and dark matter scattering. For example, there's FORMOSA and Forward-DUNE. These are the new proposals that I'm proposing to search for. One is for millicharge particle and dark matter. One is for neutrino. And I will tell you what they are. So for the scattering detector, before we get into the detail of all of the new proposal, let's look at the old one. There's many of them. And many of them, they're called like BUN or ND or this N or things. These N usually mean neutrino. And these MI usually mean main injector. And a lot of these are at Fermilab. Actually, all of these here are at Fermilab. So they are used to study neutrino scattering and neutrino oscillation, meaning that you want to see the neutrino. So you need high density to search for neutrino scattering, and you have the design to compare to the decay detector, which I will introduce later. So they are smaller because it's more complicated, so it costs more. And it's usually to study the stable particle like neutrino, dark matter, or millicharge particle. And these are the dark sector particle. If you want to search for dark sector particle, they are from the meson decay, Jordan production, or heavy meson decay. So it looks exactly like this. You have a meson decay to photon and Kaka bar. Jordan give you Jordan. and J psi give you J psi, give you chi bar. So they will produce these low mass dark sector particle to fly into these neutrino detectors. And now you can see that one of these example is this something called NUMI beam. So NUMI is the main neutrino at the main injector. So it's main injector is just literally an injector to inject the beam. So you can have a neutrino in main injector beam line. And then how does this work? So these first have a proton beam hitting the target, giving you, let's say, pion or other meson, and they decay into photon. And if you're searching for neutrino, then you have some other thing like charge meson decay to neutrino. But if you're searching for dark matter or mini-charge particle, then you have this virtual photon decay into chi bar, and you can search for chi bar. And then these things fly into your neutrino detector, and you can detect them through all these different neutrino detector. That sometimes they are liquid argon, sometimes they're scintillator. There's all kinds of different material, but that's not the point today. The point today is that you have a lot of these. You can search for the scattering of this chi, and also of course neutrino as well. But sometimes neutrino is the main motivation. And now you can ask another question. You already have this detector. How about new detector? So you can also add a new detector, which I will talk about. Okay. So let's look at one example, one model that you can probe with all these experiments. That is mini-charge particle. So mini-charge particle is one of the simplest model. It's kind of interesting by itself because it has some arbitrary mass and a small charge. So this is a breaking of charge quantization in a naive way. So in the low energy, it looks like as if you break the charge quantization because the charge is now 1/3 or 1. Okay. So if you really find this mini-charge particle, maybe it means the grand unification theory or string theory. There's some string compactification. It's possible that you break those, or you find some prediction of string theory, superstring theory. And we then have this YouTube video that talk about fractionally charged particle that is not confined. It's a motivation for superstring, like superstring theory predict that. So it's very interesting. So you can have these kind of search for all these mini-charged particle. And but today, so we're focusing on some kind of specific mass and specific charge. And usually you can just get this Lagrangian, look like this. So the mini-charge particle Lagrangian is the simplest. You have a mass and a charge. But the thing is, this is not the, what I want to say is that you can just directly write down this Lagrangian. It's not illegal. You will not be sent to jail because you break any physical law. But people don't like small charge. People don't like small number. So they come up with an idea called the kinetic mixing. So you have a photon, our standard model, gauge boson becomes a photon in the end, and a light dark photon, and these are coupled through a heavy fermion loop. In the low energy, it becomes a kinetic mixing term. It's some detail, if you're interested, we can chat afterward. And then in the massless limit, this chi become mini-charge particle. Okay. So then these things can fly into all these neutrino experiments, and you can search for them through this experimental probe. And that we did previously a search for all these kind of for the mini-charge particle in the mass range of 10 to.
Sorry, can I ask a question?
Yeah, please.
From your statement, it seems like, for me, it seems like mini-charge dark matter is just a consequence of massless dark photon.
It doesn't have to be. It can be. So
it can be.
Yeah, there's two ways to get mini-charge particle. One is you directly violate the charge quantization, which is allowed. You can have, there's no doubt. But then that will break the guts, right? So that's one way. The other way is you say, I have a massless dark photon coupled to a heavy fermion loop, coupled to photon, and this dark photon coupled to chi. In the massless dark photon limit, this chi will become mini-charge particle, and the dark photon will decouple actually.
Yeah, yeah. Now, what about massive dark photon? It seems
Massive
like,
dark photon, you don't have a millicharge particle, but you maybe have some like light dark matter that is charged under that not charged, that you have a coupling to electron. You have coupling to electromagnetic sector.
okay, okay. Thank you, thank you.
Yeah.
Okay.
Yeah, if your dark photon is massive, then you cannot get to the millicharge particle limit. Yeah, but it's still kind of similar kind of model. Yeah.
Okay.
So I will actually mention those dark photon model later. Yeah. So now you will have all these different probe for the interesting mass range from neutrino experiments. As I mentioned, you have LSND, mini-boon star, and all these different kind of probe. And that's why it's strong to search for MeV to GeV dark sector. But furthermore, you also can do the other neutrino experiment in more detail, like argon-nu. So argon-nu is a small neutrino detector that actually can set an existing very strong bound. And this is done by Ornella, Zhen Liu, and Rani. And they are using a more advanced technique to have the double hits. So because these are millicharge particles, they can hit the detector twice. And if you use these to trace back to target, then you can reduce the background. So this is a new study by them. And furthermore, you can also use some scintillation to search for millicharge particle, that you have a scintillator bar inside this detector, and scintillator bar coupled to PMT, and you can light up all three scintillator bars to give you a signature. So you can search for the correlated signature of all these three scintillator bars to give you a signature of the millicharge particle. So this is called a millican idea that I will use for my new experiment. Okay. So now I'm really using it. So the idea is to put this millican detector downstream of a fixed target. So originally, millican was put in LHC transverse regime in the atlas around the CMS, or actually it's around the CMS detector. But my idea is, why do you do it at LHC? Why don't you do it at fixed target? Because you have better intensity. So I propose to move it to the fixed target, and indeed, the sensitivity is better. So I forgot to introduce this plot. The plot is very simple. The y-axis is the fraction of the charge, and the x-axis is the mass of the dark millicharge particle. So you have a better sensitivity for the millicharge particle in the lower mass, but the millican has better sensitivity in the higher mass. So this is basically what it is. And for example, in Japan, so now we know millican, we know Fermi, that is the name of this fixed target experiment. There's also a new proposal in JPark that is doing a similar thing recently. So after our Fermi, there's also this new idea. So they are all complement to each other. But today, I'm not satisfied by just doing this in the fixed target. I want to go forward in the LHC forward regime, that you can have the best of both worlds. You can have both high energy and high intensity. And that's exactly how you do it. You put your detector literally downstream of the beam line. And there is already a regime you can do that. It's called TI12. TI12 is a tunnel. You can put your detector there, and it can search for millicharge particle. Yeah, please.
Oh, no.
Oh,
I
okay.
just interested in the name.
Yeah, yeah. Formosa means beautiful in Portuguese, and it's also an ancient name of Taiwan. Yeah.
Okay, thank you.
Yeah, and you can expand this. So there's already a tunnel here, and there's a hole called UJ12 hole. But you can expand this hole into a bigger area, and you can put your larger detector there, so they can search for millicharge particle. So these are the experimental program that you can do. And you find out that it's actually much better. So if you do it here, then you have a better sensitivity than millican and Fermini. So you have a better sensitivity across the regime. And that is really because you have a high energy and things are very collimated in the forward regime. So it's good to just do your millicharge particle search here. So you can see that, oh, somehow I cannot see my, okay, I see my cursor now. So this is across the board better. And furthermore, why is this interesting from the dark matter perspective? This is interesting because this is in the regime called strongly interacting dark matter, meaning that these things are strongly interacting, they cannot get to the underground detector. So what I mean is that, so these are millicharged dark matter. For example, if they are dark matter, they are millicharged dark matter. These millicharged dark matter, before they get to the underground detector, they'll get stuck in the crust or in the atmosphere. So they cannot reach the underground detector. And there's some cross-section, doesn't matter, there's a reference cross-section. If you plot everything in terms of reference cross-section with electron, then there's a curve that you can predict that above this curve, you cannot probe the millicharged particle with direct detection experiment because they cannot, these local dark matter cannot reach the underground detector. But all these accelerator experiment, they can probe this region because you're producing this directly. So you can help close this millicharged particle window. Okay. And this also is interesting because this is also the regime that you can have the millicharged particle to explain the edges result. Because this happens to be the perfect regime. There is some model that you can use these to explain the edges result. And I just say a few words about that. If you're interested, you can read more. So in the early universe, there's a lot of CMB photon and there's a gas. And when CMB photon pass through this gas is cold, so it will absorb some of the photon. And the absorption is 21 centimeter. That's why it's called 21 centimeter measurement. And because if you have dark matter that is very cold and it's millicharged dark matter, then you can cool down the gas more than it used to be, more than the standard model cooling. And if it's cooler, then you can have the absorption stronger. So edges collaboration see a very strong absorption signature. So they say, so people say, oh, maybe there's millicharged particle cool down the gas and give you a stronger absorption. But it doesn't have to be the case, but that's one of the explanation. And this regime happens to be the same regime. So Accelerator Probe is very interesting and meaningfully probing this parameter.
Sorry, can I ask a question?
Yeah, please.
What's the fractional FM? What's the value of FM in your model?
It's very small, right? So, okay, so it depends what the fraction you want. So in this plot, the plot is plotting 0.4%. Right, so it's very small already. So in the original plot, this one I don't assume dark matter, so it's just some millicharged particle. But in this plot, I assume 0.4%. But you can also go smaller. So depends on your model. For this specific model worked out by this group of people, they can have even smaller percentage of the millicharged particle being of the dark matter being millicharged particle. But then this also couples to the cold dark matter to to better cool down the gas. So you can have small percentage, so 10 to the minus 4, for example, like 0.1%, or 10 to the minus 3%, or 10 to the minus 5%. So even if it's a small percentage, so this tells you a very interesting thing about millicharged dark matter. Even if your dark matter is just a little bit of them are millicharged, you can still have a big effect on the cosmic measurement. So it's very significant.
Yeah, thank you.
Yeah. Cool. Okay. So FORMOSA can also study neutrino physics, which is very cool. You can study the heavy neutrino electric dipole moment. Heavy neutrino is not necessarily a neutrino. You can just say some heavy Dirac fermion, but you call it heavy neutrino because it could be a heavy neutrino. It could be a fourth sector of fourth number of the neutrino family. That's fine. So we call it heavy neutrino. You can search for it. But more excitingly, maybe you can search for a tau neutrino electric dipole moment. That would be very exciting. And why? It's because in the LHC forward regime, as I show you, there's a large flux of high energy tau. So you can really probe the tau neutrino EDM, which is very exciting and it's not very well studied. So this is a very cool stuff. And maybe you can do other neutrino physics, we don't know yet, but these are very cool and we should further study these. And I also have even newer idea to put more neutrino detector in the LHC forward regime. One idea is put a Proto-DUNE. So Proto-DUNE is the small detector that is preparing the big DUNE. So there's a lot of planning for the new future DUNE experiment, but they built a smaller one at CERN called Proto-DUNE. But now you can put the Proto-DUNE in the forward region to study neutrino physics. And this is super exciting because it's filling the gap, as I told you. In the low energy, you have a lot of low energy neutrino study of the cross-section. In the high energy, you also have a lot of high energy neutrino study. Between these, you can use the Forward Proto-DUNE or other neutrino experiment to study these at LHC. And I want to call this Neutrino Campus because you can put small neutrino detector around LHC in the forward regime to search for neutrino physics, to study neutrino physics. And there are already some idea realized, but like phaser new is one idea, but there's a lot more you can do. So this is something I'm actively thinking about right now. Yeah, with the phaser collaboration. Okay, so these are neutrino, these are scattering experiment. How about decay experiment? Decay experiment, and I will mention the
neutrino collaboration is a different collaboration than phasor collaboration. Or
it's very similar. It's basically phaser plus some neutrino people. Yeah, yeah. It's very. I think it's basically the same collaboration, but with more neutrino people adding into the collaboration. Yeah.
So you said about neutrino electric dipole moment. So what about magnetic dipole moment?
Oh, I'm talking about a magnetic. Well, oh, actually, that's a good question. Is it?
It's the same, almost the same.
Yeah, I need to think about this one. Once I think they are the same, right?
You meant the same thing. Magnetic dipole. F mu nu.
Yeah, I think there's no real difference. Yeah, I think it's also yeah, I think I should just call it electromagnetic dipole moment. Yeah. For dipole, it's really not that different. I mean, you can search for magnetic monopole. You can also search for like fractionally magnetic charge, but the model is very weird. So I don't do that. But yeah, you can search for magnetic monopole as well.
I mean magnetic dipole, maybe electric dipole moment is just a gamma 5 factor.
Yeah. Just a gamma 5. So you have a sigma. You have a sigma mu nu, F mu nu. Yeah, you have a new fermion. You have a new fermion that has let's call it chi sigma mu nu, F mu nu chi, something like that. Yeah. So yeah, so it's sigma mu nu. So I think it's the same. It doesn't.
CP violation.
Yeah, I don't think.
You have some CP violation, right?
Yeah, maybe you can add, I see what you're saying, but I think the gamma 5 will be absorbed into the. Yeah, I think maybe you can have a 2 parameter. Yeah, there might be some subtlety, but I think you can search for both actually if you have a difference. Yeah, I need to recall myself. But anyway, we can chat about this detail after. I would just call it dipole moment, like electromagnetic dipole moment.
Okay.
Yeah. Okay. So now we understand the scattering experiment. Let's look at the decay experiment. So decay experiment is kind of very different from the scattering experiment, but they also usually come with the neutrino detector. So usually you have a big neutrino detector, not a big, you have an expensive neutrino detector, and you can have a cheap decay detector attached to it. So these include CHARM, NuCal, NX62, CQuest, and DUNE. So there's many of them. DUNE near detector as well. There's a gas detector, there's a decay detector. So there's also many of them. And usually they have large decay volume, low density, simple design, and to search for decay particle. So scattering is searching for a stable particle. Decay experiment is for searching for long-lived decay particle. And it's very simple design. It's some plate and some ecal in the end to search for your energy deposition. So you can track these charged particles. So you have A prime, for example, dark photon decay to 2 lepton. You can track it by some plate, and then there's ecal in the end. So it's super simple. So now you can search for this in the NX62, and for NX62 specifically, it's searching for rare K-ion decay. But you can repurpose NX62 to be a beam down experiment. So you can make it a kind of decay detector for dark sector particle. And also there is a CQuest that people want to repurpose it into a dark sector search called DarkQuest. They want to remove the wall and put a detector here. But I think that it's more nature. Yeah, sorry.
I think, is there a real experiment or just your proposal?
So the sequence is a real experiment, but the proposal is to replace this. So yeah, this thing already exists for sure. The proposal is to remove this wall and put an ecal here called DarkQuest.
Oh, thank you.
Yeah, but I think this idea is cool, but the background will be very bad and the cost will be quite high because you have to remove the wall. So my new idea is to not do it here. So not do the DarkQuest, but do the LongQuest. When I call it LongQuest, I mean that I put a detector behind all of these things. There is this iron block, and I search for dark sector here. So I can produce a very kind of long-lived dark photon or other stuff that decays here rather than earlier. Then the background will be lower because you have iron block to block all the background. And you can search for things in a cleaner environment. So this is my idea called LongQuest, which is putting, so inspired by their idea, they want to put it here, but I just say, okay, that's actually not good. This is moving here. But I think they still want to do it here because you can search for more short-lived, long-lived particles. Like they want to search for some dark sector has stronger coupling, so shorter lived. So they want to still, so you can do both. So you can put a detector here, and there happen to be 2 detectors, so you can do that. And then other than that, I also say, why don't we add more detector? Like you can add a ring Cherenkov detector and a front detector with the new dump and the new fast tracking. So there are some, these are kind of more crazy. So this LongQuest 3 is very crazy idea to have these fast tracking and new dump to search for short-lived particle. But this is very realistic. So this LongQuest 2, I think is very realistic that you can really search for things that is decaying here. So you can see that a lot of my research program is, there's already an existing idea that is pretty cool, but I want to improve it by slightly modify the design or to do it in a better location to make the sensitivity better. So there's LongQuest detail. And now you can compare all these different experiments. They have different energy, different proton target, different distance. And you can now do a systematic study. And I'm still doing a systematic study of all these different dark sector particles. And one of these are the dark photon. So dark photon is vector. There you can do all these vectors, Higgs, neutrino portal. But one of these is the dark photon. So you have a dark photon decay to stuff, and you can search for that. So this is the kinetic mixing, A prime, and you can start to study all these things with all these big target experiment, and you want to do it as systematic as possible. But let me segue into the thing that I want to mention today. Let me check how much time do I still have. Okay, 15 minutes is about the time that I expect. Yeah. So let me segue to one of the interesting model that you can do that is related to the decay particle, but it has its own interests, which is also related to Hillman's job. And actually, I also saw other people who work on the strongly interacting massive particle. And this is one of those related models. So forget about anything I say previously, but just remember this thing I say. So I'm sure some of you are very familiar with. So you can have this, again, velocity-dependent self-interacting dark matter to better fit this galaxy profile. So again, in the galaxy that you have faster relative velocity, you want a certain self-interaction cross-section. In the lowest velocity, you have a different self-interacting cross-section you prefer. So eventually you have this kind of velocity-dependent self-interaction cross-section that is preferred to fit the data. And Hitoshi and other people, they did this resonant self-interaction cross-section model to have the resonance and to give you this kind of behavior. And the idea is very simple. The mass of the R is about 2 times of the mass of the dark matter. That's it. It's very close to 2 times. And now you can change your delta. The closer the delta is, you have this kind of sharp resonance. So when you hit the resonance, you get this peak. And that's the basic idea. Now you ask, is this model like really interesting? Like, who cares about this? Like, it's so arbitrary, right? Why do you have this resonance? Turns out it's not arbitrary. And in the universe, in the standard model, you have a lot of this resonance. For example, you have the K-on. So you can have K plus K minus go to phi, then go back to K plus K minus. And this phi happens to be 2 times of the K-on mass. So it's exactly perfectly what we want. Not only that, there's many other resonance. Another one example is the Upsilon 4s. Upsilon 4s is also 2 times of a B mass on that, which is shocking, right? Interesting. There's a reason for that. But if you just look at this, you're like, oh, it's perfect. And then you can build model for this. So we built several different models so we can link that to 5KK and the elder SIM model. But I will not get to talk about these two. If you're interested, I can tell you about the link to the elder and SIM model because I realize a lot of people are working on this here. And this is the paper. But let's look at one. Before that, let's look at all the standard model resonance. So you see a lot of these. So these one are the very significant one. These are actually, I think this triple alpha process is the most significant. Because if this is not on resonance, if this is not 0.00026, if it's 0.001, then we're not here. We cannot be here because the astrophysical process will be changed. So this is kind of anthropic principle reason why this number is so small. But there's no other reason to explain why this number is so small. So it's very interesting, to say the least. But for the meson, there's some reason I will show you. But you can see there's so many resonance in the meson that this mass is so close to 2 times of these. Upsilon 4 is so close to 2 times of B. Okay, so standard model. Let's look at actually standard model. So this plot is purely standard model. There's nothing else. So all these dots, the black dots, are 2 times of the pseudo scalar meson mass. So the smallest mass is the pion. So this the first one is this one is the pion. 2 times of the pion mass, 2 times of the K0 mass, 2 times of the D0 mass, and 2 times of the B0 mass. So you can see these are increasing like in this fashion, and they start to cross all these different higher level vector meson. So you see that the resonance, it's close to a resonance for all these different locations. And it's shocking, right? It's not that shocking. I'll explain to you why. But this tells you that resonance is because of this, because you are starting to cross all these levels. And anytime you cross this level, you have a resonance. So it's very interesting. And so let's look into the heavy quark situation that you can ask my ancestor from Fermilab. That there is Chris Quigg and John Rosner, Fermilab and U Chicago. They study this heavy quark theory. So there's different kind of vector mass-on-mass that you can predict. So they actually predict this vector mass-on-mass. And you can also consider 2 times of the pseudo-scalar mass-on-mass. They will start to cross different places. So this plot is, again, let me explain a little bit. So it's the mass of the quark. If you change the mass of the heavy quark, you can change the mass of the 2 times of pseudo-scalar mass-on. And there is also different level of vector mass-on. So when you change these, you will start to cross each of these levels and give you a resonance. Okay. So the interesting thing you find out is if you go to a higher quark mass, the larger the difference between the quark mass and lambda, the easier you can hit the resonance. So there's many level. The higher you get to, the easier you hit the resonance. So you really want the splitting between the quark mass and lambda. The better the splitting is, the better you hit the resonance. So you want it to be at least 10. So you want the quark of the mass of the quark to be 10 times more than lambda QCD, for example. So now you can build a model. We build an asymmetric model because you need asymmetry to not annihilate things away. So we build an asymmetric dark matter model. You have a heavy quark that is B quark and C quark that happens to have the same mass, for example, to simplify. And then you have a light quark that is U quark. So all these are dark stuff. Now everything is dark now. So sometimes I drop the prime, but now it's understood everything is dark. So you have B quark that is heavy, U quark that is light. And then you have all these B meson and D meson, and they have the same mass. Now, they are much heavier than lambda QCD. But then you find out there's also a pion that will happen. So pion cannot be dark matter because if pion is dark matter, you don't have the resonance self-interaction. So you need to decay the pion. So the D and B will have this resonance self-interaction through upsilon NS. And N has to be larger than 10 to hit the resonance easily. Okay. So you have all these level, and then you can calculate everything. So you want this larger than 10 to hit the resonance. And then you want the pion, the dark pion, to decay. So we allow the pion to decay to dark photon, and dark photon decay to E plus E minus or mu plus to mu minus. So this is visibly decay dark photon. So you have an interesting phenomenology because your quark mass is fixed to be 5 GeV because they are asymmetric dark matter. So you have 5 GeV quark. Then your pion mass have to be pushed to lower mass because you want it to be light. And you push your dark photon mass lower than the pion mass. So the lower you can probe this, the lower you can push your dark photon mass, the better you can have a resonance. But these interesting regimes are already being probed by all these different experiments. So this is a very significantly interesting phenomenology that you can be probed by all these different experiments already. Okay, so we're having some significant, and furthermore, let me give you a best fit model. So the best fit model would be you have a dark matter that is 5 GeV, and you want the resonance self-interaction, so you want this coupling to be 27. And it is very close to the standard model value, actually. So this is actually close to the standard model BB option 4S. So it's a coincidence, but it's a cool coincidence. So it means this model is really working. And you want the dark photon to be about 100 MeV. So this is larger than 50. So you can get a right resonance. And the kinetic mixing is around this range. Everything is good. Yeah. So maybe around here will be an interesting region. Okay. So I'm basically done with all my intro. The one last thing I want to mention is the decay detector can set a very strong bound for the inelastic dark matter. So if you have inelastic dark matter, usually you can avoid a lot of bounds. But because you have a decay detector to search for this, you can have CHARM and NuCal. They can set very strong bound for the inelastic dark matter in the MeV to GeV regime. So we did a systematic study to discover this very strong bound. This is just something I want to mention. So I want to do a more systematic study of all these decay detectors. And if you're interested, there's a lot of very interesting projects that we can study regarding to many of different models, including Relaxion, Baryogenesis model, naturalness motivated model, Quarks, Koto related model, a lot of these. And the near future opportunity, including NUMI beam, SBN, DUNE, detector. There's also a lot of low-cost alternative proposal like Fermini, FORMOSA, LongQuest, and you can also do dark sector in neutrino observatory like Super K, Hyper K, and there's a lot of new exciting searches for dark matter, including astrophysical search. Thank you. Thanks for the invitation.
Okay, thank you.
Thanks.
Thank you for your comprehensive talk. There are a lot of interesting topics. So
yeah, I hope it's not too many. I hope there's a logic that links them together.
I think that somehow they are linking between one and another. So please, now it's open for questions and comments.
Hello, I have one question or comment.
Yeah,
please.
Actually, your talk is quite interesting to me because I'm also into this region. Anyway, you like some proposal for FORMOSA. I was confused because it looks like very much to me it's like beam dump experiment. Like how is different from your proposal of FORMOSA from LHC beam dump experiment? Hello? Can you hear me or not?
Yu-Dai? Somehow he's frozen. Well, Yu-Dai? Oh.
Wrong.
I think he's coming again.
Sorry.
Okay.
So yeah, so my Fermilab laptop,
okay.
the desktop has issue that will shut down accidentally. So I prepared my laptop. So I have experience. So I have prepared my laptop. So now I switch to my laptop. But we can continue. Let me just get to the slides. But yeah, please go ahead and ask the question.
Did you hear?
Okay, I will ask again because it looks like my comment or question is like this way. Your proposals, you have many proposals like, as example, FORMOSA. To me, it's very similar to beam dump experiment.
Yes.
It's already known lots of like beam dump there. I mean, this looks like LH beam dump experiment.
Yes.
Is this same beam dump experiment or something else?
Oh, let me connect you. Sorry, it's sorry, let me make sure. Yeah. Sorry, which beam dump experiment?
I mean, there are many beam dump experiments. I mean, like, it means looks like yours are like LHC beam dump.
Yeah. So you're right. So basically, when I introduced the kind of FORMOSA experiment, it's really not a completely new proposal. It's the combination of putting a millicharged detector in the forward region, and you immediately get a sensitivity. So it's certainly not a completely new experiment. We just have a new name for the liability reason, and also to get a funding from Taiwan because the name is yeah.
I see.
Yeah, but you're right. So it is basically as I say, a lot of the things I do are not like a completely new idea. A lot of things I do there's existing good idea, but I want to make it better by consider a slightly different location or completely new location. For example, the fixed target is completely new, but for FORMOSA, it's basically moving the millicharge from the transverse regime to a better regime, to the forward regime, and your sensitivity is already much better. And the advantage is that the millicharge is already tested, so the technology is already robust. So you can already use the very robust technology and get a better sensitivity because you are now in the transverse regime. Yeah. So yeah. So, but you're right. There's already many beam down experiment, and that's why J Park, the Japanese experiment, they also want to do that's called submat. So they also have a new name. It's called submat. Let me show you submat. So I also know J Park is a K-pop star because I was searching for J Park, and there's a K-pop star called J Park. I think so. It's J Park. I think the younger people probably knows about it. Let me find yeah. Oh, it is J Park, right? Yeah. Yeah. I want to be a K-pop star one day. Yeah.
No,
So,
it's very difficult.
Yeah. So yeah. So even the submat. So this is also kind of like a new-ish kind of proposal. They just want to do it in downstream of the J Park. That's putting the detector downstream of it. So basically, they are just the millican in different locations. Yeah, if you. But of course, the challenge is different. So in one thing I want to say is that if you put the detector here, there's a new background called you have a high energy muon background, because you now have a very strong high energy muon. Then you have to differentiate that from millicharge particle. So the way to do is you have to cut down the large large photoelectron event, because when you have muon passing through this scintillator, you get a lot of photoelectrons. So you have to veto out those events. You only keep the low photoelectron event. So that's one thing. And you also have to worry about the after pulse. So there's a lot of after pulse signature that you have to, after pulse background you have to worry about. But these are just the different challenge to do it in the forward regime and in the transverse regime. In the transverse regime, there are less high energy muon, so it's less significant of a background. Yeah. Thank you.
Okay.
Thanks.
Possible one more comment.
Yeah.
It's also name of that. You say high energy, high intensity.
Yes.
But to me, it's like medium energy, high intensity.
Yeah.
I mean,
yeah.
You got becoming fixed target cannot mean it cannot be high energy frontier. It must be much lower than high energy frontier. It's just a medium energy or some lower, but with high intensity.
Yeah, I agree with you. But when I say high energy is higher than the other fixed target experiment. But in this, I agree with you that it's basically medium energy compared to the real high energy. But for the LHC forward regime, at least the collision energy is in the high energy frontier, right? Because these are really the 40 TeV proton collision. So in some sense, these are high energy high energy frontier. But I agree with you. The fixed target one is the medium energy, but I just like to call it the high energy, comparing to other fixed target experiments, because there's also electron fixed target. They are in the lower energy.
Mm-hmm.
Yeah, yeah.
Okay.
But I agree with you. This, yeah, it's easier. It's more accurate to call it medium energy in the fixed target.
So,
Yes.
do you have any more questions from other
Can I make a question?
Yeah.
You said millicharge particle, and it looks like your analysis energy is due to. I'm sorry. Let's go. If millicharged particle behaves with composite with normal charged particle, I mean, then the particle must look like a charge like 1 plus minus epsilon. So in this case, can we find something analysis? I'm sorry for my English.
Sorry. So you, I think. Let me think about this. So first of all,
Yeah.
if you're saying in the standard model sector, so there, I think. Let me make sure you're saying I understand what you're saying. So in the standard model, you cannot have mu1 to be 1.1 or 1.001 charge of the electron. The reason is these are fixed by anomaly cancellation. So because they have to be like the same, because you need to cancel the anomaly. So the anomaly cancellation will fix all the U1 charge. But I think what you're asking is the bound state. So I think you're asking is, can these millicharge particle form a bound state with charge particle? I think so. I think you can do that, but I don't think a lot of people thought about this property yet. And also, these are not neutral, so things are a bit complicated. I don't know if this will be, yeah, I think people haven't thought about this very carefully yet. But maybe they can form bound state. So I think that's possible. Yeah, I don't think there's a reason why they cannot form bound state. But these are not a neutral particle, so then there will be some weird situation. So because they are not neutral, they might have some radiation. So maybe they are not stable. So yeah, so I think they're not stable. Yeah, but yeah, thanks.
Thank you.
And normally, if dark matter is charged, then it might form a bound state. So normally, there's a strong bound from unstable composite particle searches. So as I remember,
yeah, I know there is something called opuranium or something. So it's searching for the exactly some kind of a bound state with the like small charge particle thing, but those constraints are in the lower mass end. So there are studies like that, but I think recently nobody really did the bound state study properly recently.
So yeah, I think that there might be a little bound maybe for in the case of millicharge particle. So it carries a certain charge maybe, but I haven't thought about that much.
Well, by the way, Maxime has an interesting paper yesterday about the millicharge particle being stuck because they lose energy and they stuck in the Earth. So maybe they can form some kind of bound state. I don't know what they will do, but they can stuck in Earth, like because they got slowed down, right? So you have local millicharge particle dark matter interacting with the atmosphere and crust, and they just lose energy, so they stuck in the nearby. Or in the crust. Those might have some interesting phenomenology. Yeah,
I see.
So I have a simple question.
Yeah, okay.
What's the production of your millicharge dark matter? Because I have never done in millicharge.
Yeah, it's super simple. It's very simple. So basically, anything that give you electron or muon, you can also give you millicharge particle. Because they are basically a heavy muon or heavy muon with a small charge. So the production look like this. So the production include this Dalitz decay. You have a pion decays to photon and 2 millicharge particle, or Joyen production directly QQ bar annihilating into Kai bar, or J side. Yeah.
My question is not this the collider production. Like my question is, what's the radical density production?
Oh, radical density production is much more complicated. So that's a good. So one thing you can do is you directly annihilate. So you can directly do the WIM millicharge particle freeze out. But those are very ruled out. Those are very hard to exist because the cross-section is too large. So one of the way you can do is you have another mediator, of course. So one of the model that people recently considered is you have additional annihilation process. I think I have a some here. Yeah. So this is just one example, but you can first have a coupling between the millicharge particle with the baryon that it give you a millicharge. But then this thing then also couples to cold dark matter or other sectors, so you can do the freeze out. So So this is one of the way to get the small millicharge particle. Yeah.
Okay.
But it's not very pretty. It's not a very nice model. Like millicharge dark matter doesn't really have a nice model. But you can also just think about one way is to you can have a small fraction of these millicharge particle produced in the supernova or things like that. And that's being considered right now. I'm also thinking about this. But then they're not really the freeze-out mechanism. Sorry. There is one model. There is one very good model. That is the freezing model. So if you like the freezing dark matter, freezing model can give you millicharge dark matter, but the cross-section is very small. So the cross-section is way down. So it's way down. Not this regime, it's much lower. Yeah. But I can show you some paper about it. So yeah, you can produce millicharge dark matter very well through freezing, but the cross-section is very small. Yeah.
Okay, thank you. Thank you.
Yeah, thank you.
By the way, what is the region in direct detection in this plot? It's below. It's here, right? It's the region for direct detection is everything. Sorry, I'm not familiar with this. Yeah, it's everything. It's gray area. The gray area are the direct detection. Below this critical reference cross-section curve, and also the RRS and XQC. So XQC is a rocket experiment. They have the direct detection experiment on the rocket, and RRS is on the balloon, so they can search for direct detection of the millicharge particle. So it's but the small cross-section, you are excluding that region by direct detection.
The larger, the smaller one, yeah. So there is a regime. So the direct detection, I should show. There is actually a plot. So because of the attenuation above this curve, you cannot search for millicharge particle, but below this you can search for it. But then when you go to very small, then the bound disappear again. Then you go near to the freezing curve. So if you keep going down, you eventually hit the freezing curve. But the direct detection bound goes away because the cross-section is too small. Yeah. So there's a medium regime that look like this that direct detection can search for. Yeah.
So I have one more question, maybe then after next person could ask. So in your resonant dark matter model, the dark matter is the baryon in your case?
My dark matter is the pseudo scatter meson. So it's not a baryon, it's like a pi kind of stuff.
Pseudo-scalar measure. So then is it stable? Is there any reason for them to stay stable, to be stable?
Yeah. So I can show you. So actually, let me go back to my big. I'll show you. So first of all, if you just make them a pion, then they're stable, right? Because they are the lightest one. So you can just make them pion, right? So you can just use for example, you can have two flavor. Let me actually directly show you the plot. So let me go to connecting, joining. Okay, so let me show you the SIDM. Yeah. So let me stop sharing here, but open another one here. Let me turn this off. Can you hear me? Hello?
I cannot see your screen yet.
Yep, good. So let me open it. So yeah. So I want to show you the model. Oh, sorry. Let me stop this for now. Okay, good. It's open. So you can now really build the model. So yeah, you're asking if this can be stabilized. So one of the model you can build is the model.
Sorry.
So the model look like this. U quark and S quark. Just 2 quark, not 3 quark. Just U quark and S quark. Dark quark, of course, and they become kaon-like particle. But this kaon is kind of like pion because they are the lightest pseudo-scalar meson. So they will not decay. So you can have K plus, K minus annihilating into phi kind of particle, which is SS bar, and then give you K plus. So this is one of the model, and then we have that in the paper. And you can also have energy annihilating through dark photon. So this is one model. Another model is the model is not stable, but it is stable because it's asymmetric. So the other model that we have is you have asymmetry. So you have a C quark and B quark. They are C quark, and then they combine with the U quark, right? So these are stable because they are asymmetric. So they are asymmetry. So they will not annihilate away with each other. They cannot annihilate. But in this theory, there will be a particle that is lighter, that is pion. So you need the pion to decay. So we induce the decay through decaying through, because you don't want the pion to be the dark matter, because now you want to use the heavy quark to be the dark matter. So you want the pion to decay, that's why you have the pion decay to dark photon. So this is the second model.
Oh, I see.
The third model that is directly linked to your model, your self-inheriting massive particle model. So the third model that you, or the one that Hitoshi and other people work on, that is kind of Wessel-Witten term model, right? So again, all pion, but you have more complicated sector. You have, let's say, 2 flavor, and then you have a complicated gauge boson broken to give you the Wessel-Witten term. So now this is interesting because now you can have the 5 pion theory. And then you can then also do the lattice study. So people actually do the lattice study, and they find out that in certain parameter, when your m pi over f pi is 1.9, you actually do have a vector meson that is roughly 2 times of the pion mass. So everything works out. So you can have the 5 pion self-interaction. You can have the vector meson resonance through some lattice study that there's some detail here. But then this model doesn't work because the 4 pion self-interaction is too strong. So you get ruled out because the 4 pion is too strong. So you have resonance is good, but the 4 pion is too strong. So they basically get ruled out, but maybe not completely ruled out because the study here is very complicated. So maybe it's not completely ruled out. But if you believe in the fit by the previous group, then they are ruled out because they're the small 4 pion interaction. So basically, they are basically ruled out. So this is the story of the
this latest result is from the Korean group, right? So
that is
some of the people
maybe,
in this.
I think maybe. So I know Lee is from Taiwan, but Lee might be from Korea.
Hong and Lee, yeah.
Oh, I see. So it is from Korean group. I see.
Yeah.
Oh.
Thank you. Yeah, thank you for your sharing the details.
Yeah. Sorry, my desktop died, so. But I prepare my laptop, so it's good.
Okay. So there are more questions. Also. Okay.
One last comment.
Yep.
Yeah, you discussed about this magnetic moment. Not the electric dipole moment. For the magnetic dipole moment, you need sigma mu or something like tensor-like new interactions or spin interactions. If we cannot some control spins, you cannot measure this magnetic dipole moment. Maybe you can have something like indirectly. It comes with the magnetic dipole moment and you can measure. But it is very indirect and much with the model dependence and much smeared out, so you cannot do that. best way you have to make something new physics which is spin dependent or some tensor-like interactions. Then you can do something for the magnetic dipole moment, I think.
Yeah, I think you're right. I need to think about it a little bit more. I haven't thought about, but I think maybe you're right. If you add more, if you have a tensor-like interaction, yeah, I need to think about it more. But yeah, I think you're correct. I have not thought about it enough yet. Yeah.
So okay. Have you thought about transition dipole moment, like from neutrino to heavier neutrino?
Oh yeah. So we thought about it in a different kind of different paper. So we thought about the heavy neutrino transition dipole moment. So you can produce this heavy one and then decay back. Mm-hmm. So that one we studied the neutrino experiment for that kind of transition dipole. Yeah. Mm-hmm. So that was studied. Yeah.
I see. Because recently there was a serious study in connection to xenon one-ton anomaly.
Yeah, I have a paper on that actually.
Oh, you have also.
yeah.
That's good.
I think. Dipole.
It will be another talk, right?
yeah, I have a paper on that. So are you talking about this paper or there's another paper about it? Oh, there's actually two or three papers about it.
I think I remember your paper also, and then also there's some serious paper from Sun Group. Joachim Kopp also.
Yeah. Joachim did a much more detailed study.
Yeah,
we did a very
BB and CMB constraint.
Yeah, they did that much more in a more complete fashion. We did a very kind of more preliminary study focusing on xenon result. Yeah. So it's
probably in your case, FORMOSA or LongQuest could constrain further more parameter space also, right?
Actually, maybe it can. Actually, you're right. I haven't thought about it, but maybe it can, because you have a lot of these neutrino flux. So actually, you might be able to do it, but the signature will be different. So I wanted to send this, but maybe I need to. Oh yeah, I need to. So it's this paper. I wanted to. Yeah, and also the following paper by much more detailed study by Joachim and other people. But yeah, and FORMOSA might be able to study this. It's not the strongest thing because FORMOSA likes to study just the dipole. So you can just study if you just have a neutrino itself and have a dipole, that's good. And you can also study the heavy one, but this is an upscattering. So it will give you a lot of photon, probably too much photon that you'll get vetoed out, because that might become a background, right? Because you have upscattering and give you a high energy photon. Then the photon will light up the whole scintillator bar, which will be the same as the, let's say, muon background. So that's harder, but it could still study that, because if you have a very high rate of that thing, then maybe you can, if you have a very high rate of that thing, you can set a constraint. So it's possible. Yeah. If you can control the background very well, it's possible you can study that. Yeah, I haven't thought about this, but you can do that actually. Yeah.
Is FORMOSA is under review at the moment, or?
So not yet, but it will be, because I think eventually, as we discussed previously, I think we will just directly merge with the Minicharge, because Minicharge already have everything. So they will just, so right now the current idea is that we will just take the Minicharge prototype and put it in the forward region in the tunnel for the run 3. So right away, you can do that right now. You don't need new detector. So you can already get the prototype, put it in a TI-12 tunnel, and you can directly do a study. But then in the future, we're trying to get money to build more new experiment like FORMOSA in the tunnel and in the bigger facility called Forward Physics Facility. So that is, we are trying to get funding. So, but that's tied to the snow mass process. So yeah, something we're trying to do right now.
Okay. So LongQuest.
By the way, can I have this slide?
Yeah.
Copy of slide?
Yeah.
Yeah, sure.
Okay.
So this.
Thank you.
Yeah. I'm going to
Now,
share.
please send it to me. Yeah, once you have the file, please send it to me so I can see that.
Sure. Yeah. I think Hyung-Min will share.
Sure. So we are going to, we are recording this seminar. So even you can see this on video. And also
When you send the slide file, please let me know link of this record too.
Yeah, everything you will have.
Okay, thank you.
Okay. Are there more questions? I think we are pretty have a good discussion until now, but he has a lot of content in the top. So
Or too many, but I try to have a lot
more questions or something to discuss. Yeah, to ask. I think it's good. Yeah, I think that we have good discussion until now. I think now, yeah, it's time to close our session. Yeah, thank you very much for your nice, interesting seminar.
Yeah, thanks a lot, and thanks for the questions. Yeah.
Okay. So let's keep in touch. For collaboration and discussion.
Yeah, let me know if you accept me. Good.
Okay.
Well,
I will study your talk and your papers more carefully.
Yeah.
Let's discuss. Okay.
Yeah. Thank you.
Okay. Thank you very much. Okay. Bye.
Bye.
Okay.
Bye.
Bye.
Bye. Bye. See you.
Thank you.